Dear participants and organizing committee of the KSEM 2021, I would like to welcome you to the presentation of our research on improving answer type classification quality through combined question answering datasets. My name is Aleksandr Perevalov. I am a PhD student at Anhalt University of Applied Sciences. We have done this work together with my scientific supervisor, Andreas. Now let me introduce the agenda of this talk. So, at first, I would like to introduce you to the topic, including knowledge graph question answering and the expected answer type classification itself. Thereafter, I would like to talk about related research. Then I will introduce you our approach. After that, a significant part of this work is data preparation. So I will give an overview of available datasets. I will talk a little bit about how did we unify class taxonomy. Thereafter, I will explain and introduce you the experimental setup that we created here in this work. Then we will talk about the analysis and discussion, including the effect of class distribution mismatch and impact of class distribution on classifier's accuracy. And thereafter, I will conclude the talk and talk a little bit about the plans for the future. So, what is question answering? The modern question answering could be divided into two paradigms. The first one is the information retrieval based that works mainly over unstructured or semi-structured data. The second one that we are working on is the knowledge-based question answering that works over structured data, for example, knowledge bases, databases, or knowledge graphs. So the goal of such system is to map a textual question to a semantic representation of a query to a knowledge base or a database. For example, if we ask in what city was Angela Merkel born, we expect to see something like this. It can be a logical query as the first one. It can be a Sparkio query as the second one. It can be whatever you want, SQL, for example. But in the context of this talk, we are discussing only knowledge graph question answering, which is a subset of knowledge-based question answering. But what is the expected answer type classification in this context? So just imagine again this question: in what city was Angela Merkel born? And of course, we here expect to find an answer which has a type city, for example, Hamburg or something else. If we apply it to one of the famous ontologies, such as DBpedia ontology, we expect to see an entity of type DBO city. The second question is, did Italy win Euro 2020? Obviously, we would like to hear yes or no. So this is a Boolean expected answer type. The third example, what is IMDb ID of Quentin Tarantino? Here we expect to see an answer of type string. But what is the motivation for the expected answer type classification? Just imagine again this question: in what city was Angela Merkel born? And here I would like to introduce you the size of search space without expected answer type and with expected answer type. So obviously without expected answer type, we would like to query all the one-hop nodes, all the nearest nodes related to Angela Merkel in our knowledge graph. These nodes can have type place, string, it can be people, organization, or dates. So this search space is very, very wide. However, if we know the expected answer type, we can significantly narrow down the search space to something like this. So here we have places that we can rank in order to get the answer. If we transfer it to Sparkio queries, we will see something like this. So without expected answer type, our system will produce the query as you can see here on the left side of the screen. The number of retrieved results is 861. However, if we filter these results by an answer type of city, we will receive only 6 results, which significantly narrows down the search space and optimizes the answer candidates list. What are the research questions that we ask here in our work? First one, can the expected answer type classification quality be increased by combining previously isolated datasets? So that means that datasets that were previously used separately from each other. And secondly, what are the characteristics of the appropriate or inappropriate training datasets? So we would like to investigate specific characteristics that can improve or decrease the quality here. Our main contributions are as follows. We proposed an approach for improving the expected answer type classification quality based on effective reuse of existing datasets. We derived 4 new expected answer type classification datasets. We gathered several insights from the influence of the training data on classification quality. So let us talk a little bit about related work. The first big block is related to entity-oriented search. In this context, expected answer type classification is sometimes referred to as target type identification. Here, two models were produced, entity-centric model and type-centric model. Entity-centric model is not applicable to our field because it first requires to retrieve the entity list, rank it, and thereafter retrieve its types, as you can see here on the screen. However, type-centric model is something different. It works as follows. The textual description of all entities that belong to an answer type T are concatenated in a large pseudo-documents, like this one. And these documents, therefore, are ranked with respect to an asked question. The second block of the related work is contextualized ranking of entity types. The approach on the left side uses named entities mentioned in a question to get the additional information about their types and therefore to make a final ranked list. On the right side, the approach also uses the information. In addition, it uses the linguistic knowledge and knowledge from unlabeled sources such as word embeddings. The final block of the related work is semantic answer type prediction task, which is a competition for expected answer type classification. This competition showed that extreme classification outperforms information retrieval-based methods for the expected answer type classification because the first place was taken by exactly this approach. Secondly, it showed that transform-based architectures outperform other ones, so the first 3 places were occupied by transformers. And finally, you can recognize my surname here. We took a 3rd place in this competition using our multilingual data augmentation approach, which is also an option for this task. Let us move to the approach that we will introduce here in this work. Here we took several datasets that have corresponding training and testing subsets. For the training subsets, we make a power set of all of the datasets, and we use all of these parts of the power set to train our language model and therefore to test them with the testing subsets. Thereafter, we have these predictions that are analyzed. Let us talk about the data preparation. We used several famous question answering and one question classification dataset. You can see that these datasets have different structure, have different sizes, and therefore they has to be unified such that we can use them for the expected answer type classification. The class ontology should be also unified. That is why we decided to use DBpedia ontology top-level classes plus some primitive classes in order to cover everything. We had 2 steps in our answer type retrieving approach. The first step is dedicated to retrieving an answer URI itself. Thereafter, we retrieve the type of the answer URI. Several datasets provided us with the SparkQL query. Some of the datasets provided us already with the answer URI. So that is why we used first and second step for the first 2 datasets, RC-Quad and QOD. Because the track 50 dataset is already question classification dataset, we just mapped its classes to the DBpedia ontology. Web Questions doesn't have either SparkQL query or answer URI. That is why we manually labeled this dataset. Simple Questions provided us with the Freebase URI. That is why we used only second step here. Overall, we got the following picture. Here you can see the dataset that we have obtained during our data preparation approach. Of course, some of the data was lost here. For example, for Simple Questions, we have lost some data because not all of the entities are interlinked from Freebase to DBpedia. And of course, you can find the obtained datasets in our repository. It is available online. Let's move to the experimental setup. As we mentioned before, we used the power set of all considered datasets to train the model. So in total, we had 31 training sets and 5 corresponding test sets. So total number of the experiments for each model is 155. and we used 3 pre-trained models. The full experimental results are available by this QR code. But now we would like to see some of the significant insights that we have found here in the analysis and discussion section. In this table, you can see the aggregated results by number of training datasets in a combination. First, what we recognized is a consistent quality improving trend with the addition of external datasets. If you see from the left to the right side, the quality always increases. The more datasets are combined to create a training set, the more robust are the results with respect to the standard error. So the standard error is decreasing on average. However, we always would like to know the information for specific cases. Maybe sometimes there are outliers, maybe sometimes the quality drops when we append other datasets. That is why we ask us a question, does increase of training dataset size always leads to directly proportional quality growth? So firstly, we would like to introduce our findings related to effect of class distribution mismatch. We used Kullback library divergence to measure how class probability distribution of one dataset is different from the another dataset. For example, on this heat map, you can see the corresponding values of Kullback library divergence. The LC quad train and LC quad test value is quite low, which corresponds to a very similar class distribution. On the other side, if we compare simple question strength and LC quad test, then we can see very high value, which corresponds to very high difference between these two datasets. Obviously, we would like to know, is there a correlation between these values and the classification quality? That is why we have done several experiments and we found out that there is a strong negative correlation between Kullback library divergence and the F1 score. That means the more is the class distribution difference between train and test set, the less is the quality. The Kullback library divergence can be also used for other multi-class classification tasks, not only for expected answer type. The Kullback library divergence value represents the possible improvement that we can achieve by adjusting training dataset class distribution such that it is more similar to the test dataset class distribution. Our second finding is related to the impact of class distribution on class bias accuracy, so the accuracy for individual classes. Here, for instance, we used web questions and track dataset for training and simple questions for testing. In the parentheses, you can see the corresponding KOD values with respect to simple questions. On this chart, you can see the class distribution of web questions and track dataset. Obviously, the distributions are different for some classes. For example, place class is very different, word class or topical concept also different. But what is the impact of this difference on the correctly answered questions for each class? Here we can see a number of correctly answered questions given the web questions dataset, track dataset, and track plus web questions dataset. If you consider a point of view of web questions, for place class, we had 6,598 correctly answered questions. After we concatenated track dataset, this number was decreased. However, if we take a point of view of track questions, we can recognize that this number was increased. It is also the same for some other classes, for example, topical concept. This leads us to a conclusion that combining datasets may improve classification if a significant difference in class distribution between training and testing sets is observed. So the appended dataset can strengthen the distribution for specific classes such that the number of correctly answered questions is higher. But if we are not sure about the class distribution of an external dataset, to summarize the analysis and discussion, we can say the following things. On average, the more data is used, the better the quality and more robust the model. However, we always would like to know the information for specific cases. That is why we use Kullback library divergence as a measure of difference between class distributions. We found that Kullback library values have negative correlation with F1 score. That means the more difference between class distributions, the less is the quality. We observed that combining trained datasets may be worth only if train and test class distributions are similar or test distribution is unknown. On the other hand side, that we combine trained datasets with class distribution that are different to the test distribution, then it could lead us to a quality decrease. One of the main conclusions is that by utilizing linked data model, we can create a large synergy effect between related research tasks. So here we used question answering datasets. Using linked data, we transformed them to expected answer type classification datasets, and thereafter have done our experiments here. Thus, we encourage other researchers to use this model in order to increase the reusability of the research results. Of course, our work has several limitations. The first one, we used only top-level ontology classes. They are too general. The second one, the approach was not compared to existing benchmarks, for example, SmartTask. Of course, we used only English questions. This is also a limitation here. And finally, we didn't use other ontologies for the classes. So only DBPT ontology was used. Consequently, we have the following plans for the future work. We would like to extend granularity of the ontology classes and possibly solve a hierarchical expected answer type classification task. We would like to apply the approach and its insights within SMART 2021 competition. And of course, the approach should be extended with respect to the used languages and class ontologies. For example, we can use Wikidata ontology. We also had some improvements in our work in the following dimensions. As we mentioned before, we participated in the SmartTask competition where we reused only part of our findings, but nevertheless, we extended our approach to hierarchical multilingual expected answer type classification, which is available now as a demo here. You can scan this QR code and you can use this demo. You can provide some feedback for our predictions. It will also help in our future work. So I would like to conclude my talk and say thank you for the listeners. Thank you for your attention. If you have any questions, you can directly ask them here, or you can use the following contact information that you can see on the slide. Thank you very much. Goodbye.